We've covered a lot of ground on regularization, from understanding its fundamentals to exploring advanced techniques and real-world applications. Now, let's bring it all together and recap the key regularization techniques that empower machine learning models to be accurate, robust, and generalizable. Because at its core, regularization isn't just a tool, it's a mindset for building better models that thrive in the real world. At its heart, regularization is all about preventing overfitting. It ensures that models don't just memorize training data, but instead learn generalizable patterns that can handle new, unseen data. Whether it's a simple linear regression or a massive deep learning model, regularization is the key to achieving balanced, reliable predictions. Let's break down the major techniques we have explored. L1 regularization, Lasso L1 regularization adds a penalty equal to the absolute value of the magnitude of coefficients. Key benefit: promotes sparsity by shrinking some coefficients to exactly zero, effectively performing feature selection. Best use case: high-dimensional datasets where irrelevant features need to be removed. 2. L2 regularization. Ridge L2 regularization adds a penalty equal to the square of the magnitude of coefficients. Key benefit: stabilizes the model by penalizing large coefficients, preventing over-reliance on specific features. Best use case: models prone to multicollinearity or when you want to reduce overfitting while keeping all features. 3. Elastic net regularization. Elastic net combines both L1 and L2 penalties, balancing feature selection with coefficient stability. Key benefit: handles correlated features better than L1 or L2 alone. Best use case: datasets with many features, especially when some are highly correlated. 4. Dropout in neural networks. Dropout is a technique where a random subset of neurons is dropped out, set to zero, during training. Key benefit: prevents over-reliance on specific neurons, forcing the network to learn distributed, robust representations. Best use case: deep learning models, particularly in image recognition and NLP tasks. At this point, you might be asking, which regularization technique should I use? The answer depends on your model and data. If you're working with a linear model and have many irrelevant features, L1 regularization can simplify the model. If you want to stabilize a deep learning model, Dropout and L2 regularization are great choices. For ensemble methods, techniques like feature subsampling and early stopping keep models efficient and generalizable. Regularization isn't just a technical adjustment, it's a foundation for building scalable, trustworthy, and high-performing AI systems. It ensures that models are robust under real-world conditions, able to handle messy data, changing trends, and unpredictable challenges. Whether you're working on healthcare, finance, NLP, or autonomous systems, regularization is what transforms a model from good to great. And as machine learning continues to evolve, so will regularization techniques. The question now is, how will you use these tools to build the AI systems of the future?